Hello everyone. In this video, we are going to look at another well-known optimization algorithm, which is typically used for multi-dimensional functions, multivariable functions, as long as it's unconstrained and unimodal. This is called the Nelder-Mead Optimization Method or Nelder-Mead simplex optimization method. Just need to mention that a few of the pictures are taken from this great book, Numerical Methods Using MATLAB, by John Matthews and Curtis Fink. So, what is this method? As I said, this method works for unconstrained problems. It works in multivariables. Typically, it's very good until the number of variables is up to 10, no more. After that, it becomes quite a bit slow, and the multi-surface that the simplex is moving on is going to be very complicated. The best thing about it is it does not use derivatives, as opposed to gradient descent or steepest descent and Newton method that uses the double derivative as well as the first derivative. This method only works with function evaluations and no derivative. So when there is no underlying function on where there is a lot of noise and you don't want to perform derivative, this method is your choice, okay? As long as I said, most of the time it's a unimodal in that region. It doesn't need to be unimodal in the whole search region, but at least unimodal close to the search region that you are starting your initial guess. Okay, and I'll show you that because we're going to see that here in this example or another example. I'll show you this guy here. This function has 4 basically minima. And depending on where I start in which one of these basins of attractions, the simplex is going to converge to one of them. Okay, so it doesn't need to be globally unimodal, just locally. Now, for that reason also, as we're going to see later, it will converge locally, not globally. So it will converge to a local minima, not global one. It's a single particle optimization. It's not a population method. So it only has one simplex rolling down the surface. Therefore, it will be susceptible to being trapped in local minima. And if you have flat surfaces, this method may stagnate and not move. Okay, so there are a bunch of things that we said, and as I said, it's really good for 2 to 10D. Okay, so once the number of variables is more than 10, this is not going to be ideal. And there are a few other things that we need to talk about, but as I said, the biggest thing is no derivative, which is really great. If you remember my previous video that I published, the name of it was Golden Section Search Optimization. That was similar to this in terms of not needing derivatives. It only worked based on the function evaluations, but that one was only for 1D functions, a single variable. So this is the version that needs, it can work on multiple variables. But the essence of these two methods are completely different. It's not like this is an extension of that, no. So, how does this method work? The idea in this method is the notion of simplex. And simplex is in the ND space is basically n plus 1 vertices that are connected together. For instance, if your function f is a function of x and y, so you have 2 variables here, your simplex is going to be 2 plus 1 or 3 vertices, which becomes basically what? A triangle, right? Or if you are in the 3D space, so you have a function of x, y, and z, so you have 3 variables, then you're going to have something that had 4 faces, and you know the name of this guy is called a tetrahedron, right? So tetrahedron in 3D, and as you go above that, basically, it's not one of the shapes that we know because we cannot even imagine that. So in general, we form this one. And if I want to explain it very, very simply, if I want to explain it extremely simple, so if you look at a cross section of this, right, so it's something like that, Basically, this is like you have an object that looks like a triangle and you let it roll down the surface. Okay, so you let it roll down. It's not perfect roll down because, for instance, you see that some of the bad points are going to be mirrored with respect to the average of the two good points or something, but it's kind of similar to this guy rolling down and ultimately ending up here, maybe something like that, or ultimately laying flat like this. Okay, so it's the idea of rolling down a surface, but the thing about this triangle is the size of it can change and the shape of it can change. So the movement of that mostly coming from this idea of reflection, but the size of it can extend in one direction. We call it expansion. It can shrink in a direction or contract in a direction. So the shape of this, as it moves on, it can be basically it can be more kind of extended in one direction. It could shrink, become smaller. There are lots of things that happens in this algorithm. So let's go ahead and see how this method is exactly working. So what are the steps that you take in this algorithm? So let's say here your simplex has basically from 1 to n plus 1, it has n plus 1 vertices, right? Yes? So let's say if you are in 2D, you are going to end up with 3 vertices, x1, x2, and x3, right? So let's say n equals 2, for instance. So you have a triangle, something like this triangle WBG. And these are those pictures that I said coming from the textbook. So if you have this triangle, you are going to now sort these points based on the value of the function at these points. You sort them from the smallest to what? To the largest. Okay, yes? So x1 is the point that has the minimum value. In here, we call it B, which means best. Then the point on the right side is the point that has the biggest value, and you want to get away from that point because here the goal is, by the way, when we say algorithm, here we are talking about minimization. So these steps that you see is to minimize a function. You might say, how do I maximize it? Well, you just minimize the negative of f. If this is a vector, right? So if you minimize negative of f, that means you maximize the f. So you can use it for both cases. Now, as I said, you have some best point, and here the reason we are using 2D or n equal 2, so we can imagine that and show it to you. So let's say this is your xn plus 1, this one here, that's your worst point. x1 is the point with the minimum value, that is the best you have. And then you have a point in the middle, which is not the best, not the worst, and this is the good point, G. Good. So now, the first thing you do, you exclude the worst one, and you calculate the centroid of the rest of the points. In this case, we are showing it by m. Okay, so this m, or x of c in this formula, that is the centroid for all points except for the worst one. Now, what do? The goal is to replace this worst point by something better than itself. And the idea is, let me go ahead and reflect this worst point with respect to this centroid point m and put it to the other side of it, right? So you're going to reflect w with respect to m, and you end up with what? With the reflection point. Now, you might say, is that such a good idea? Well, actually, if you look at here, you can see that it could be. For instance, if I want to go with you over this cross section, look here. So let's say we have something like this, for instance, something like that. My triangle is like this at the moment, right? Or let's not put all of them at the same level, or two of them. So let's say something like this. So what are these points here? This point that has the lowest one, this is your best. This point that is the highest one, that's your worst, and this point here is the good. And let's say this is the centroid M. So you reflect it with respect to this, and you're going to end up here. So this is going to be your XR, your reflection points. In those notations, in that triangle, that was basically R, correct? So you see clearly that by reflecting the worst point with respect to the centroid of the rest of the points that are better than that, now I have this new triangle, which is between B, G, and R, and hopefully the position of this black one is better than what the red one. It's getting closer to this minimum point here. Okay, yeah. So you get this reflection point, which can be calculated by mathematically as x of the centroid, in this case m, plus a coefficient alpha times x of c minus x of n plus 1. And most of the time, this alpha is taken to be 1. So it's exactly mirror image of that. Is it? Yes. Why? Look here. If you look here at this picture, this vector inside x of c minus x of n plus 1, in this case, is m minus w. So it connects w to m. So that's this vector. That's this one here. You multiply it by alpha 1, so it's going to be the same thing, and then you add it to the m. So if this is like, say, the origin of the coordinate frame, this is the vector for xc in this case, or m. So to this vector, you're going to add that guy. And if I move this vector here, shift it like forward, so I use the triangular addition of vectors. Now this one here and this one here is going to take you directly to the reflection point, right? So it's a simple vector addition here, basically using a triangle method. Okay, so we got the reflection point. Now what? We're hoping that this is better than the worst one, right? So here we have to do a bunch of comparisons. Now we have to come and look at this reflection point and compare it with everything that we had earlier to see where this new point, the f at this new point is compared to the previous f's. Is it better than the best one? Is it somewhere between the worst and the good, between the good and the worst, or even worse than the worst? Okay, so we have to look at different scenarios, right? Which you can see here, there are 4 different scenarios. And for each one of these 4 scenarios, there is a suggestion in this method what to do. So first says, if the new point, this reflection point, is better than the second good point, but not as good as the best point. So it's clearly better than good and worse than everything, but not the best of all. It's not beating even the best one. Accept it. Definitely accept this new point. Okay? Now, that means now your triangle is gonna be between B, G, and R as opposed to between B, W, and R. So now keep moving with this one forward. Now, this is if it's between what? Between the best one and the second to worst, somewhere between them. And this is, remember, this is second to worst, not the worst one. Now, sometimes it's so good that it's even better than the best one. So I think personally, I believe that actually we have to really bring this beforehand. But the thing is, we cannot talk about expansion if we don't talk about reflection. So a specific scenario here is it's even better than the best one that we have. Then what would you do? We know that this direction that we are going, this direction is such a good direction because the new point I got in this direction is even beating my best one. So I say, if this direction here is such a good direction, why don't I move further in that direction? So what do? Look here. Instead of stopping at R, I'm going to further expand it. Okay? Yeah? So here I say, x of expansion is x of the centroid plus gamma, a parameter gamma, times x of the reflection minus x of the c. Okay, and x of reflection minus the c is this vector here, right? This vector. I multiply that by, again, gamma. Many times this gamma is considered like 2. So you see, if there was a d, I add another d, and then I add it to the centroid, and that is going to give me this new point here, which is called expansion point. So now that the reflection point is there, it's calculated, the centroid, I know it, and gamma is, let's say, 2. Now I'm going to go one further distance d, or whatever the distance is between this centroid and this reflection. I go one more units in that direction, okay? And that puts me further down in this good direction. Hopefully this expansion is even better than the reflection one. But you only do it when this reflection is even better than the best one. If it's not better than the best one, and it's worse than that, but better than the second to the best or something, you only go with what? You only go with the reflection point, okay? So on the left side, this triangle here in red is going to be your triangle, but if you have expansion, now this guy here is going to be your triangle, okay? So it depends on where the reflection point is with respect to everything else. Good. So now let's move on and see different other scenarios. So here it was better than the best or somewhere after the best, and definitely better than second to the worst. Now, what if it's not that good? So here we have two other scenarios. Sometimes this reflection point is better than the worst one, but not better than second to the worst. So it's just better than the worst one, nothing else. If that happens, then you define a new point called the outside contraction point, which is equal to x of the centroid plus a parameter rho times xr minus xc. What does this one do? Well, if you look here, if this is r, instead of staying at r, it says go back a little bit. You went too far in this direction. Go back a little bit, right? You beat this worst one, but you did not even beat the good one. So go back. By how much? By 50% go back. So this rho that you pick here is typically what? About 0.5. Hey, you moved too much in that direction. Go back half of what you came. Come back here. And stay here, so now your triangle could be this one. Now, we get the new point x of c outside. Are we going to use it? Before we accept it, we have to check something. We have to make sure that this contraction point, this outside contraction point, got us a better value than the reflection one. Because reflection already bets the worst one. So if this one is better than that, even if it doesn't beat the second worst, but still better than the reflection, I'm going to accept it. And as I said, I'm going to go with basically this triangle. Good. If it doesn't have this contraction, does not give me an improvement, then I directly go to the last step, which is shrinking. Good. Now, this is the scenario that the reflection point was between the second to worst and the worst. Sometimes the reflection point is even worse than the worst. This is like the worst case scenario, that you got the reflection point, you did not do any good, you got even a worse result than the W. Then what? Say, well, guess what? You should not go in that direction at all. That was definitely a bad direction to go. Guess what? Go backward in that direction. You're going in the wrong direction. Don't go there. Move back, turn around and come back. How much would you come back? Again, typically come back by 50%, but instead of going away from the centroid, come back toward the worst point, go midpoint, somewhere in midpoint between the worst and the centroid. And this is called the contraction point inside. And the formula for it, if you look, is very similar to the outside one, except for positive rho times that is negative rho times that, so it's going to be backward. So in this case, you say, hey, yeah, your reflection was horrible. Come back, look at this midpoint here, x of c in. Now, would you accept this x of c in? Again, we have to compare it against the worst one. If it's better than the worst one, yes, we accept it. And now my triangle is going to be this one here. But if it's not, then I go for shrink again, right? Now, what is the shrinking? The shrinking says, hey, I got the reflection point, which was worse than the worst point, and both of these contraction points that I got, both either or one of them at least, the inside and the outside contractions also failed. They didn't make it any better. So now go and do a shrinking. What does shrinking do? Let's look at the formula. It says x of I equals x1 plus delta x of I minus x1. What does that mean here? Look what it does. So here, remember, you had the best point, you had the worst point, you had the good point. What would you do? You take each and every one of the points that you had except for the best one, you move them back toward the best. So you take this good one, and along this line that connects the good to the best, you go backward in that direction. And this worst, along the line connects it to the best, again, move this back toward the best. So W end up at S and G end up at M here. And this delta parameter is also typically 0.5, so means move 50% back toward the best one. And now your triangle, instead of this big one, now it is going to be this smaller one here. So your size of the simplex is going to shrink here. So this is the expansion, contraction, reflection, and shrink. Different operations that you do on the vertices of the simplex based on the value you got out of the reflection step. Okay, now before we look at the MATLAB codes that I made for you, let's talk about this a little bit. So as we said, this method is a local optimizer, not a global one. It can, if it goes to flat surfaces, it can stay stationary and stagnate. It works well as long as the number of variables is from 2 to 10. Another very critical thing about this method is scaling. Scaling is crucial. What does that mean? Well, look here. When you are doing your optimization, let's say here you have two independent variables, x1 and x2, you want to make sure that the total range of x1 and the total range of x2 are similar. You see here, for instance, x1 goes from -6 to 6, and x2 also goes from -6 to 6, so they have similar scales, so this is going to be good. But if one of them goes from -6 to 6 and the other one goes from -60 to +60, so one of them is 10 times bigger in scale than the other one is, then the surface, the shape of it is going to change, and that can create very narrow passages or very, very flat valleys, and that is going to make this method not perform very well. So you want to make sure that the scaling of the parameters are at a similar, so you might normalize all of them, for instance. Another thing is, if your algorithm is failing, it's not converging, it's stagnating or something, you want to restart it. And by restart means your initial location of what? The initial location of the simplex. You started somewhere, right? Go ahead and start it with something else. Change your initial condition, okay? Now, where would you put this initial condition? Either start it from the current best point that your current run gave you, or just go ahead and give it a perturbed random point, okay? So if it stopped, but you found so far that this point was the best point, now go ahead and start there. or make it completely random, or perturb this point, which means go a little bit around it and then start from those points, okay? And this restarting hopefully gives you a better chance of moving down the hill and going toward the minimum. Now, this method has alternative algorithms, including pattern search and the CMAES, or Covariance Matrix Adaptation Evolution Strategy. A big name. If I have time, I will cover one or two of these, but these are some alternatives for this method if it's not performing the way it should. So now let's go ahead and look at the code. So here, this is a custom Nelder Mead that I wrote to run on this function called Himmelblau. Okay, seems like a German name to me. And this function is this guy here. It's a basically 2D with two variables, and that's basically this one here with these 4 minima. And we're gonna run it on this one, and we're gonna see the animation of the simplex as it moves from the start point toward what? Toward one of those final minima. So this does a good animation job for you, and I'm gonna share them under video description with you. The other one is, I don't know if I told you or not, I guess I did in the beginning of the video, the function fminsearch in MATLAB does use this method. So if you look at the documentation of MATLAB, fminsearch is using this method. So you can pass it the function, you can pass it the initial guess and the options, and this is going to return anything that you want, including the minimum point, the value of the function and the minimum point, an exit flag, which if it's 1 means it was successful, otherwise not. And then you can get the outputs at each iteration if you ask for it. And once you get those outputs, not just the very last value, you can basically also do an animation as well here. And you see the options I'm using is display iter, so it is going to show on the screen the value at iterations. I'm giving it a absolute tolerance, a tolerance for the function, a maximum iterations. The output function is outfun, and the plot function is basically optimplot fval. Okay, so here you see that this optimplot fval is basically a built-in function that will plot for you the optimum value and so on. But this output function is some function that I made here that keeps the values and can generate the animation for you. So let me first show you this custom one. That is my favorite one. So let's take a look. And by the way, the function I'm minimizing in fminsearch is different from this one here. There we go. You see, it started here, it changed, it basically moved toward this goal point and stopped. And you see that basically the value of it changed. Here it doesn't print anything, but if you want, you can add some fprintf, so you can have the final value, right? So you see here this best. This is your point. If you want, you can print it on the screen. And the other thing is, here when it says draw now, you can slow it down. So you can say, hey, give me a pause of, I don't know, 0.2 seconds or something. Slow it down. And as I said, for this best one, you can go ahead and print something on the screen. Okay, I changed the code a little bit. So now it slows down so we can see it. And in the past, the code used to create an image of the final result and save it to the local folder with I am right. Now I removed that as well and basically show the final value where the function is converging to. So the value of the function and the location of that minimum. Okay, so this is optimum value, of course. So let me run it one more time so you can see the result. You see? You clearly see the size of it is shrinking, changing, and you see the reflections and so on, expansions. and I started here, and it is going to that place. And after the threshold that passed, so the value of the function is barely changing. You can see that here. Now it is going to stop, and this is the final result. Right now, if I want to change the location, it was at 5 and -5. So I take it to -5 and -5. Look what happens. I put it on the left side. You see? Now it is converging to the one that is here. Okay, so it depends on where you start. If I make it like -5 and, for instance, -2, you see that it should converge to this one here, and I can start for something on the other side too. So here, this one needs to go below 10 to the -12. There we go. So this is the other minimum point. This is the value of the function added. And as I said, let me move it up a little bit so you can see it converges to the other point. Well, actually, it was +2, not -2. So like this. There we go. You see that how this method is working here. And I can, for instance, start something here like 3 and 5 and show you that one as well here, right? So let me show you this one as well. And you can see that it is working to one of the corresponding ones. There we go. Look. Now look at here. Did you see what it did? So first expanded big time, and now it is shrinking. And you see that it is slowly going toward that minimum point here. And of course, it is facing a more difficult path. So this is going down, but takes quite a bit of some time. And if you zoom into that region, you see that there is still a simplex, and it is going down, but almost now it's a perfect point because those points are very close to each other. Okay, and you see that now it converges to this point, 3 and 2, and the value of 0. So this is this code. And then if I show you the one that is using MATLAB built-in function, which is fminsearch, now here the function is different. That is this hard function called Rosenbrock, which is one of the hard functions for optimization. And again, here is going to do something similar, except you don't see the simplex here. You just see the, as you can see, the centroid of it. Look, so I started here, and it is going inside this very narrow kind of valley, and it should move gently and come to the minima that is here on the right side of it. And because of this narrow valley that it has, this function is a hard function for optimization. Okay, it's not in a place that is easily accessible. So it has to reach somewhere here. And you see it is doing it gently and moving toward there. You see the value of the function still big enough, but as soon as it gets to this region, this one starts going down faster. Right? So you see now it is getting smaller and smaller. The minimum is at 1 and 1, and you see that it is going to get smaller. And probably after 120 something iterations, guess what? It stopped. And now it says that, hey, the value of the function is at 1 and 1. The minimum value is almost 0. The exit flag is 1, means it was successful. It took 118 iterations, and these are the values of the function at these 118 iterations. So we started at 62.5, and we went down to almost 0. Okay, so this is that show iter. This is that option here. So I'm gonna share both of them with you under the video description. Hopefully you learned something about this very important and useful optimization algorithm, and I'll see you in the next video. Thank you.